Do we need to, because this is connected? So ask. Hello, is there anyone on Zoom? Yeah, we have time. So someone on the Zoom, can they please confirm if they can hear us? Okay. Okay, thank you. Good afternoon. Welcome to Lab 2. And hopefully you guys are on track with all the homework and part 2 of homework 1. We'll be going through some details about network optimization, which will helpfully benefit all of you. So as we all know, data is a very important part of everything that we are doing so far. It can have various forms, and as we have in the first, we have speech. And the next homework you'll have images and so on. So I just need like a raise of hands of how many people have started working on P to have finished their early deadline submissions. Okay, fine. So does anyone want to tell me what kind of data do we have in first homework? NCP? Just missing one letter there. Yeah. So what are these MFCCs? And what is the actual data we are actually training it on? What are we trying to do? So we are basically trying to work with speech. And if I record my voice like this and then do some training on that, will that help? Like how will the computer actually interpret that? And so we have to do some kind of pre-processing because we cannot use the speech directly. And that is why we have converted it to MFCCs. MFCCs is Mel frequency cepstral coefficients. Now, again, to go more into detail about that, you'll be able to read about it in your write-up. And if you have any doubts about it or want to know more into detail about that, you can obviously come to our office hours and we can tell you more about it. But for the scope of this homework, we have already done that part for you. So we have already converted it from the speech to MFCCs. And then on, you have to do all the other things. So let me tell you one rule of data science in general. You need as much data as possible, and data is never going to be enough, right? And the more data you train your network with, in most of the times, that is going to give you a better performing model. So what do you do in cases when you do not have enough data? Yeah, so we generate more data from whatever we have so far. And this is what we call data augmentation. We do nothing but augment the data that we currently have. So this can be done in various forms. If you have image data, for example, there is a lot of things you can do with it. You can rotate it, flip it on horizontal, vertical axis, change their brightness level, add some other kind of noise, and so on. And how does this help? Anyone want to answer that? Okay, so the one of the major goals of training a model is to increase the variation. Okay, so to make it generalize better. So for example, I want to detect a chair over here, right? But is this the only kind of chair available in the entire world? No. Also, is this chair always going to be here only? It can be outside a different light setting, right? There could be something placed over the chair. And so we need to find such kind of data, and it's not possible for us to get images of every possible variation. And so what we can do is we could generate this kind of data. So if I take an image of this chair and increase the brightness, that will give me another of the same chair, right? And so we'll have some extra data. So this is the kind of stuff you could do with images. When you come to speech, we do not have any visuals, right? So in that, what we do is these MFCCs and everything that deal with frequency data, and you have some kind of timeline, right, when you speak. So what we can do for augmentation there is work in these areas. So we can sort of mask a time, we can do either time frequency or we could, time masking or frequency masking. So what we do in this is over time, we mask a few instances of time or frequency and we feed in the same data. So that is the kind of data augmentation you can do. Also, this will depend a lot on the task at hand and the data and the kind of data you're dealing with. But this was just sort of an overview of what we call augmentation. Other thing is that the data sets that we get and the data we have in that, they could have different scales for each feature. A simple example would be if you're trying to deal with student data, we could have a feature regarding the age. We could have another feature, say the number of subjects that the student has taken, right? And so the range may vary a lot. A student could be between 20 to 30, but the subjects that they could take is mostly like 5 or 6, maybe not more than that. And so the scale is very different. And when you want to train these features, you do not want that the scale of this feature affects the model training. So if, for example, some feature has a very high scale, you do not want it to be more important while it is getting trained. And so we do data normalization. Now, there are various types of normalizations, and there are various ways in which we can do normalization. A very simple one would be take all the features, see whatever is the maximum value of whatever feature, and then divide all features by that maximum value, right? That is your min-max scaling. You have the normal z-score normalization or standard scaling methods, and you can obviously explore more as you do the homework. One of the normalization methods that will be very, very helpful in homework 1 is cepstral mean normalization. So this has to do with the cepstral coefficients that you get in your MFCC data. And what this does is it makes your computation very efficient, first of all, because you are normalizing it, and it makes your data very robust. So it is trying to basically minimize the distortion that is created by noise. So what it tries to do is that if you have speech data, it should be invariant to the person who is speaking it, because you want to focus more on what is being talked about rather than who is saying it. So stuff like that can be normalized using cepstral mean normalization. And it is one of the best kind of normalizations used for speech so far. So what we basically do in this is the kind of, so the kind of pre-processing we have done in this homework is MFCCs. We've given you MFCCs. So part of it is already done, right? So we are using MEL frequency cepstral coefficients already. So now for the cepstral mean normalization, what you need to do is normalize these coefficients. So how do we do normalization? Just like the simple form of getting the mean and variance and doing your normalization. But what do we use? The cepstral coefficient. And that's why it is a cepstral mean normalization. So again, we will be talking about a different kind of hyperparameters and a lot of other things that matter while training. But how do we actually come up with the best performing model? So if you're not familiar with this word, ablations is just trying different kind of combinations, different kind of architecture with different kind of hyperparameters together, and sort of giving all possible kind of combinations to sort of figure out what works the best and analyzing all those results. So by tomorrow, no, by Monday, you all should be filling your study group forms, and by Tuesday or Wednesday, you should be allotted a TA, and also you'll have your own group to do all the ablations with. So what you'll ideally be doing is with your group of 4 people, you'll each be taking one kind of combination each and running those ablations. And then collectively as a team, you'll figure out which part works the best, right? And then you can have another iteration of ablation from whatever insights you got from the first one and get a better performing model. So does anyone want to tell me what would be a good model architecture? Come on, it's not that difficult. At least, yeah. Okay, why? Okay. So, okay, the general notion, diamond, I would still want to know after this recitation why you came up with just diamond. But a general notion is that the deeper the network, the better it is at predicting things. Okay. And I would say it is not completely true. Not not every time would you just increase your depth and get a better performing model. You need to understand what kind of data you are dealing with, what kind of task you are dealing with, and what would actually matter. And also what compute you are running it on, right? Making it deeper means that you are actually increasing the number of parameters, and that would take a higher computation time also. So you need to think of that complexity too. Now, there are various kind of architectures, and the shape itself, the way you visualize it, will tell you the name of it. So diamond over here looks like a diamond, right? And then you can have pyramids, either one which has less neurons to start with and more to end with, and the opposite. You can have cylinders, hourglass, and so there are all these kind of architectures, but as we see, all of this depends on the width and depth of the network. And this is what you'll have to figure out. So if you want that the model should carry more information towards the beginning, right? You would want something that is wider at the start, and then it sort of bottles down on its features. So if you have something that some kind of data that you want to get more features from, you probably want to get a more wider network at the first, and then it should bottle down on the most important features by the end. But again, this is just one way to go about it, and you cannot really tell. So one practice would be to try all these architectures one by one in your ablations and sort of figure out. So for example, in your first ablation, you figured out that diamond is working better than the other architectures. Then you would go on one more step and see which hyperparameter, which optimization would work better in that case, right? Which augmentations. So this is all you could experiment with. You would have your shape of the network, how deeper or wider the network could be. And also as and when you will be doing all these experiments, you'll figure out that you'll come across a lot of problems. One of them would be vanishing gradients, right? And then you would want to figure out what would you do for that. So ReLU or GeLU are kind of activation layers which will help you avoid problems like this. And we'll obviously come to batch normalization and dropout later. But these are the kind of things that you will need when you are fixing your architectures in general or figuring out what is giving you a better learning. So we know what are optimizers. We know what is learning rate from the lectures so far. So learning rate is basically how big do we want the step to be when the optimizer is trying to optimize the network, right? And what we ideally want is that the learning rate should be high enough so that we are not going too slow, but we want that when we are approaching the global minima, we want the learning rate to be lower, right? But we do not really know when we are actually reaching the global minima, right? We don't know where the local minima is, when the global minima is. So what we might want to do is we might want to schedule this learning rate. So maybe at one point I want it to be very higher, but gradually I want it to decrease. It could be over some steps. So some fixed number of training steps. And this is where your step LR could help. It could also be that you want the learning rate to reduce by a multiplicative factor, but after each predefined milestone, this could be a multi-step LR. So the implementation of all of this is available in PyTorch, and you can always refer to the documentation if you want to implement any of them. They will all have their own kind of parameters that they will take in. So multi-step LR over here takes milestones. So what it's saying is that after 8 epoch, after 24th epoch and 28th epoch, I want the learning rate to decrease by a factor of 0.5. So if you can see over here, at each of these milestones, the learning rate is decreasing. What also is something that you can explore is exponential LR. It's nothing but the LR decreases exponentially. And then you have cosine annealing, which sort of follows your cosine graph when it tries to take up this value. So again, this will have its own parameters, ETM, and like what is the minimum learning rate you want it to go to. And Pmax is that, so this is what the cosine annealing graph actually looks like. But in how long do you want it to go from like the maximum to the minimum is your Pmax. So, yes.
Way for us to figure out what scheduler to use? Like, is it based on the data or based on what should be our outcome? Is it a classification or regression? How do we decide which would be the best scheduler to use?
Right. So it will also depend on your optimizer that you will be using, and it will definitely depend on the task. It's not that simple to say which one works the best, because then we wouldn't have so many kind of schedulers, right? But I think in most cases, people would like to start with either a step LR to see if decreasing the learning rate after a certain amount of like training steps or something, is it giving better results or something? Or there's one scheduler called reduce LR on plateau. So whenever your whatever metric is not changing. For example, you want that you should lower the learning rate when your validation accuracy is getting higher or not changing, right? So it means that your model is not learning. So you maybe want to go a little lower on the learning rate. You're probably approaching like the global minima, right? So at that point, you wanted to go lower, which is good. Like you will be end up using reduce around plateau a lot, but again, it has its own parameters that need to be set properly. So it has patience, right? So after how long do you want it to start decreasing, and so on. So at one point, I feel that if all these schedulers have their own pros and cons, and it also depends personally what you are comfortable with. So cosine annealing also helps a lot. Yeah. Yes, so I think you will get a better understanding of this when you are actually doing your appellations. So Adam W, for example, would work good with a certain range of learning rate, right? And I wouldn't say whether it is lower or higher because I want you to figure it out through the appellations. Yeah, but you'll understand. So the range of learning rate which works best for a certain kind of optimizer, for example, would be dependent on that, and so you'll use a scheduler according to that. But again, schedulers like reduce around plateau is just like very simplistic. It'll reduce when certain metric is plateauing, so that can be helpful in all cases. And cosine annealing again is something that increases with time. So it goes lower, and then if you feel like your model isn't learning enough, it might just take it up again and then lower. So it helps in a lot of cases. Even cosine annealing has worked a lot. And when you start working with the schedulers, will you get to know that there's so much to experiment with. So for example, over here, the max for the first sort of wave is like way higher. So the second one, you can set it to be like 0.5 of that. Like you don't have to go to the very max. Right. So these are some things that you can alter when you're using these schedulers. So whatever you are comfortable with in the end is what you'll end up using. So that's that. Now, uh, so the simple thing we saw earlier was like trying to avoid problems while you are choosing your architectures. We also mentioned batch normalization over there. So batch normalization is nothing but normalizing the batch of inputs to eliminate any covariate shift. Now, how this helps is that it enables higher learning rates. So what happens is that if you choose learning rates that are very high, it might scale up all your layer parameters, right? And when you are doing the backdrop, your model might just explode. And that is not what we want. So with batch normalization, what we do is we normalize the scale of all these parameters. And so when we are coming back in our backdrop, the scale wouldn't be an issue and your model will not explode. Right? So you want to use batch normalization in your architectures. You need to figure out when and where, but that will depend on your application. But this is something that will be helpful and you incorporate. Again, because we are using a higher learning rate, it will help you converge faster. And what we actually do in batch normalization is that for each training example, we are also seeing other samples in that along with it. So again, it's not just dependent on one of those input samples, and so it also helps generalize the model better. So regularizing it better. Right? So there are multiple advantages of it, but there are also a few disadvantages. For example, it has poor performance if the batch size is not inadequate. Sorry, it is not adequate. So, for example, if the batch size is too small, then what is it even normalizing on? Like the samples in it might not have a variance of their own. So we might not get as a good regularization, and so it might not perform as well. Also, the running mean and variance might not be the best way to calculate for like sequential algorithms like RNN because they are like time dependent. We might not want to just club it and take a normalization step. So this is where layer norm can help, which calculates the variance of each item within the batch. So for example, the earlier we were doing it for like the entire batch, like the input samples, but now we'll be doing it for all the parameters within the layer. So every time it comes to a layer, all the parameters within the layer will be normalized. Again, what kind of normalization will help is something you need to figure out when you're doing your ablations. Also, you will be able to refer different kind of papers which give you architectures like ResNet or ConNext or whatever, and you might want to explore there how they use it and in which cases it is essential. And there are a lot of other kind of normalization methods, and all the papers are already linked over there. So you can just explore, and any doubts, you can come to us for our office hours. These are some other widely used normalization methods like weight normalization, which normalizes the weight of each layer, or the group norm, which actually does the normalization for a mini batch rather than the complete batch at one go, and instance norm, which normalizes the parameters across the individual channels or features. So this is about normalization. Now we move forward with hyperparameter optimization, and Harini will take you through.
Okay, does anyone know what a hyperparameter is? I expect one person to answer. Okay, guess not. But you have two types of things that you usually have in models, right? One of these are parameters, which the model itself learns, and these are your weights, your biases, and stuff like that, which will happen through backdrop, for instance, while you're training process. These are not things that you set. But then there are hyperparameters that you would specifically set, that you would tune during your ablations, which typically control how well the training happens, and also to a certain extent how well your parameters themselves are learned. In a lot of these cases, these will help improve accuracy, better your convergence, and of course, you have certain cutoffs that you need to cross. So choosing the right hyperparameters will really help you have really good architectures, really good optimizers, schedulers, because all of these have different parameters hyperparameters that will be tuning. And so they'll have better performance in general. There are a lot of hyperparameters that you would typically tune. Some of these you would have already started doing during your ablations for homework 1P2. So you will want to tune your batch size if your model is training very slowly. Maybe you want to increase batch size, or if you're running out of workers to train on, you want to reduce batch size. Similarly, there's learning rate, which we'll see in a little bit how that influences training. Then, like Jill mentioned, you have schedulers. We'll talk about dropout, optimizers, and weight initialization, but these are typically the parameters that you would want to start thinking about when you're tuning whatever you want to tune for 1P2. So weight initialization is actually a very nice method in order to tackle any exploding or vanishing gradients. And the good part is PyTorch provides you with a lot of different types of weight initialization techniques. You have uniform, Gaussian, K-mean, normal, and all of those. I would strongly recommend trying at least a few of these in 1P2 as well. Some of them are known to help because the way you initialize weights also plays a huge difference in how your model will converge. You can't always initialize them to zeros. Sometimes initializing them in a particular way by sampling them from certain distributions are known to converge and give you better results. So do have these as a part of your ablations as well when you're trying to cross cutoffs. The next one is learning rate. So I think we've spoken about this in the earlier part as well. So it's a very important parameter in determining whether your model diverges or converges. So if you can see in these graphs, and this is something that you'll go into a lot of depth in the upcoming lectures, but if you have a very slow learning rate right from the beginning, your model is going to learn by a very small amount. And you will typically notice that if your accuracy is increasing by like 0.001% or even lesser sometimes. Or in certain cases, you'll see that as soon as you start training, your loss goes to none almost immediately. While that can have a lot of other reasons, one main reason is if you start with a very high learning rate, like for, I think your homework one, if you start with 0.1 with certain optimizers, you'll see that your loss is actually going to none. So you have to find a trade-off where if this is something that you're trying to, get to, if this is the minima and you start somewhere here, what is the step size you start with? If you start with a very large learning rate, it can just overshoot. If you start with a nice learning rate with a scheduler that reduces at the appropriate epoch, then it will start moving like this and reach here. So it typically depends on what type of scheduler you use, what optimizer you use, but it's very important to kind of start with the right learning rate. So just keep an eye out for that. So next, coming to optimizers. So again, during the training process, you have forward passes and backward passes. And what happens in the backward pass is that's when your weights and the biases and the model parameters in general are updated. And how well this entire training process happens depends on the optimizer. Again, you have a lecture coming up very soon, which goes in depth into each of these. But for the sake of this lab, as well as for your homeworks, how do you typically know which optimizer works well? And the only answer to that is through ablations. So every optimizer, the choice that you use, of course, it depends on the task that you're trying to solve, the data that you have. So it's very important for you to start off with an optimizer. And then the minute you see that, okay, either loss is going to NAND, for instance, or you see that, well, this is not working really well, you need to identify those points. And the way you would do that is through weights and biases, which again, we'll have a quick walkthrough in the upcoming slides. But having or tracking 1dB graphs is not simply because we've given it to you in the starter notebook. There are reasons that you have to do it. And one of them is to typically identify whether this optimizer is working well for my problem, whether the scheduler is decreasing learning rate at the right time. So in general, you will see that Adam converges very quickly. And if there are different variants of Adam, like Adam W and Adam P, that I really recommend you guys try out. But in general, if you look at the papers of SGD and Adam, SGD, it says that it finds minima faster purely because of its stochastic nature. But of course, please do try all of these and don't take whatever is given here for granted. Have all of these as a part of your ablations. And like Jill mentioned, everyone in your study group should take like different types of optimizers and, just give it a shot. So another very common issue that you'll look at in any of your part twos is overfitting. You will see that the validation score or the accuracy is like 80%, but when you submit on Kaggle, it's, I don't know, 50 or 60. And this is just assuming everything is fine, your code is fine, and your notebook is great. In such cases, obviously what is happening is you are running so many ablations that you're overfitting even to your validation data that you have, because you want to get the most out of the parameters that you choose, the hyperparameters that you choose, the architecture that you have, and the validation data set that we've given. So even though it's supposed to be very close, there are chances where sometimes you'll just see that your validation loss is suddenly shooting up while your train loss is going down. So you're trying to overfit, and that is being seen by not getting very good results. So in such cases, you apply techniques like regularization, and one such way is through dropout. So whenever you build your model architectures, you'll typically have a linear layer, there'll be an activation layer, then you'll have a batch norm layer or whatever normalization technique you have. Another layer that you can use is a dropout layer. Again, it's your task to figure out where you want to use, but typically what dropout does is it takes probability as a parameter. And let's say 0.3 is the probability. What happens is after the layer that you use the dropout in, it's going to drop 30% of your nodes and only consider 70%. So at any point in time, it's not taking all of the nodes into consideration, and it takes different set of 70%. And what that means is, as much as you're trying to avoid overfitting by not letting it see all of the data at every single epoch. If you train it for like 100 or 150 epochs, then having dropout is a very good idea, because eventually you don't want it to have access to all the data all of the time. And for 1P2, this will help. So definitely do add these when you construct your architectures. There are other techniques. One is early stopping. So when you see that eventually your training is saturating, your accuracy is not improving, you can literally stop it and change some parameters and then continue to train again. But what are these parameters that you can change? For instance, if you're using data augmentation, in this case, if you're using time masking or frequency masking, or if in your homework 2, you'll use different augmentation types like color, jitter, and things like that, which will become clear later. But typically, you can stop it, increase different types of augmentations. You can decrease your dropout rate or increase dropout rates, and then you can continue to train. You can slightly increase your learning rate and then continue to train. There are a lot of things that you can do, but early stopping is one way to tackle overfitting. There's also gradient clipping. So once you see that there are ways to identify when your gradients are exploding, and one of that is when your loss starts shooting to nan again. In such cases, you'll see how certain types of architectures are very useful to handle this. Specifically in homework 3, you'll be looking at recurrent networks and how to deal with these type of issues. So any questions so far? Yes. Mm-hmm. Yeah, that's a good question. I think so right now the search space seems enormous, right? There's just so much to try out. But once you start doing things, the search space will actually narrow down a lot. So if you think about it, let's say you have 3 different types of optimizers you want to try, which is Adam, W, and SGD. And you have different learning rates to try, different schedulers to try. But the minute you see Adam is not working, I would suggest just drop that search space temporarily and move to Adam W and see if that is good. So once you fix, this might not be the best way to do it because there are a lot of different parameters that can change, but there is a priority in which you'll figure out that, okay, Adam W seems to be working well. Okay, SGD seems to be working well. Let me try tweaking the learning rate, for instance. And then you'll get an intuition for, okay, for this kind of data set, it looks like if I use this optimizer, this range of learning rate seems to be doing okay. But you should know that all of this, again, depends a lot on what architecture you choose, right? Because all architectures are not going to have the same type of optimizers or the same type of schedulers. So I would say initially, yes, you will have to run quite a few ablations, but as you run, your intuition sort of develops and you can sort of start dropping things from your third space instead of still continuing irrespective of whether it works well or not. Yeah, I would say at least for homework one, part two, pay a lot of attention to getting your architecture right. Like you can fix maybe the default learn optimizer and pick one scheduler and try to get a good hold of your architecture and then try to work through the rest. But we've seen typically that getting the right architecture is plays a very important role.
Is there any way to determine the hyperparameters or make a choice based on the data, like the type of data?
Again, I would say it's only through experimentation. Like there's no way you can look at a data set and be like, hey, I'm going to use 0.5 as my gamma for my scheduler.
Like something like images or audio files or whatever. Can we make a choice based on that type of data? Like for audio files, we know this scheduler or this optimizer works the best, or for an image, this works.
Yes, after the first two homeworks, you'll be able to make that decision more clearly because there are specific sets of optimizers and schedulers that work really well for homework one and homework two. And homework one is speech data and homework two is image data, which is why I'm telling you this. But once you finish these two homeworks, I think at least I feel that I have a lot more intuition as to what works well for what type of data. So you'll definitely get that as you move through the homework. Okay, so let's go through some general homework part two tips. So has anyone here implemented mixed precision training? Nice, okay. Okay, I would strongly recommend you do this. It reduces your training time massively. So what it typically does is in PyTorch, most of your parameters while training would be stored in floating point 32, or the precision in your float numbers would be 32 bits, which is a lot. So it takes up a lot of memory, it slows down your training time. And if you want to use very large batch size, it will just speed up your memory and you'll see your RAM crashing very quickly, which is something I think a lot of you would have seen. So one way that you can tackle this is during training, implement what is called mixed precision training, where you take all of the weights that you currently have, convert them to a 16-bit floating point precision, and then you do all your forward pass, backward pass, and all of it. And at the end, convert it back to a floating point 32 precision. Will there be a loss of information? Yes, but the trade-off is huge in the sense that you have faster training speed. So if something's taking 40 minutes, we've seen things take like 15 to 20 minutes, which is a huge save of time because you've just seen the search space, right? It's a lot. So you need to be able to do all of your ablations quickly. And then lesser memory usage, and it also lets you have a larger batch size to have a faster training. So do implement this. We have given code on how you can implement this. Most of this you can just pick and use in your part twos as well. So if you haven't implemented it, I strongly recommend that you implement it before you start any hardcore ablations because it will reduce your training time. One thing to remember is this note, it will not work on all GPUs. So if you use very specific types of GPUs, it will not work. We've seen that it works for T4, V100 and A100. So if you're using these three, definitely implement mixed precision training. Okay, so in general, I think this is sort of a summary of things that we've spoken about. Don't try all possible architectures on your own. Tuesday or Wednesday, you'll get study groups. You'll also get a TA mentor for your study group. Each of you should pick one type of architecture and you should try different types of optimizers, different types of schedulers. If you sit and do 100 ablations, I'm not going to say it's impossible to cross cutoffs, but it's very taxing. It's a lot of effort and it's much easier if you just divide things amongst your study group, talk to each other, what works well, what does not work well. And then when you see that something is working well for someone, you can, let's say someone finds out that, oh, this particular architecture works well. Then you can take that architecture and try different schedulers, for instance. You can try different optimizers. You can try different bits for the same type of architecture. So there's a lot of different ways that you can tackle all of these part twos. We support healthy collaboration, so do make use of your study groups as much as you can. And try to explore different strategies, explore different hyperparameters for your homeworks. Another thing is constantly monitor your training on Collab or AWS. I know this is something that we all do, as in we try to constantly do it. Whatever happens, we just go back and try to keep looking at it. Don't try not to do that, like run something and you can always do something else in the background. Don't get very anxious about, if your performance is not great. Start early, you can always come to OH. You can, post stuff on Piazza. We're happy to help you out, but yeah, just things to keep in mind. It is not impossible to cross the high cutoff. It is very possible. A lot of us have done it. So if you have any issues, please attend OH. We'll be happy to help you out. And we'll soon be releasing the low and medium architecture cutoffs, but you can look out for a post on Piazza, but this will be close to the deadline. So don't just wait for that. Start your ablations as soon as possible. Okay, we sort of covered this, but yeah, on Tuesday or Wednesday, you'll sort of be getting your study group allotments. Okay, so now let's talk about weights and biases. Has anyone here started looking at your graphs in OneDB? Okay, what are some typical type of things you look for when you're looking at these graphs? Mm-hmm. Yeah. Anything else that you look for? Exactly. Yeah. I think these two are pretty much bang on how OneDB helps. So in general, there are certain things that you need to be looking for. A is when your accuracy is plateauing, you know that is when your model is not learning anymore and you need to do something differently. B is it lets you compare different runs, like what was just said. So you know if some architecture is working better, or if some architecture is so bad that it's like half the performance, just drop that architecture and try something else, or change that architecture to have deeper layers, wider layers, as long as you stick to the parameter limit. So the best way to use this is to sort of have one project on weights and biases for your study group, and all of you can log your graphs onto the same account. So that way you'll see different team members' graphs, and you can also set up your logging in such a way that when you click on any one graph, you see what layers they've used, what activation functions they've used. It all depends on how you log it. So do go through documentation on how to effectively use OneDB and try to make the most out of this setup when you're especially performing ablations as a part of your study group. And a lot of you have also been asking, how do you store model checkpoints? This was a recommendation that we had given in the starter notebook, but we're not giving you any code for it. So let's say you're using GCP or you're using just the normal Collab or Collab Pro. You can use what is given in the top right. So basically, the torch.save command will save your model state dictionary, optimizer, scheduler, and anything else that you want to. And you use torch.load to load all of these in the same way, and then you can continue to train. And then with a simple OneDB.save, this will basically save the same model onto your project as well. So you can actually go download your model, or when you're resuming any run, you can, instead of storing it locally, you can directly read it from OneDB as well. So there are a lot of ways that you can store model checkpoints. Do it this way, go through documentation, but I strongly recommend that you store model checkpoints. In a lot of cases, even with me, what has happened was, I don't know if a lot of you are using GCP, you run out of your region's resources very quickly. So you'll randomly get messages like this region has no GPUs right now, try again later. In which case, what I used to do was delete the instance and start another instance. But you can't do that if you have all your models stored in the GCP instance, right? So either store it on Drive or log it on OneDB so that things are safe. You have all of it. Even if you want to delete any instance and continue training again. You have everything that you need to do it. So remember to always store artifacts and have a good version control mechanism. So another thing that you can use weights and biases for is for sweeps. So we spoke about hyperparameter tuning, right? This gives you a very convenient way of doing it, where you can give in the form of a dictionary what different types of optimizers you want to try, what different learning rates, batch size, and all of that. But the more you increase the size of this dictionary or add more values, it's going to take a longer time. How to implement this and how exactly this will tie into your P2s. You can go to that collab notebook for code that you can use for this. And there's also a video that we have linked, which you can go and see how to conduct this sweep and what are the pros, what are the cons, whether doing it on your own is better, whether doing it this way is better. It's mostly like a design decision at this point. You choose what is more convenient for you. But do have a look at this, and if it's something that interests you, one or two members of your study group can potentially try this. Okay, so now coming to the last part, some tips for homework 1P2. Note that whatever we have spoken about until now, you can still use for 1P2. This is more specific is all. So we've seen a lot of questions on Piazza. I think many of you are shuffling the training data set, but you're also shuffling the test or validation. Please do not do that. Remember to shuffle only training and keep the other two constant. The other thing that we are seeing is a lot of you are running into NaN loss issues, in which cases either we have seen that your learning rate is very high or you're not using batch norm layers. So remember to incorporate these two in your model architectures and in your entire training process. Choosing the right batch size is very important. Some of you have tried extremely large batch sizes, and either your RAM has crashed or you get, I think, the PID workers exited unexpectedly or some error like that. So in those cases, either reduce the number of workers in your data loaders or reduce your batch size, or you'll need to do both and you'll have to continue training. Another thing that you can do is ensembling. You'll learn this again in the future, but basically you just take different models, try to put them together and see if they work better together than individually. Of course, you have to remember that you stay within the parameter limit, but this is something that you can definitely explore. While evaluating, although we've given you the eval code, I think while testing, a lot of you have forgotten what mode it needs to run on. So remember to read the starter notebook clearly, what comments have been given, and try to fill in your test functions appropriately. Experiment with schedulers, like we've always said. And whenever, let's say you train once, you figure out that there's some error, you make a change, you train again. Try to delete all your occupied memory using these commands and then continue to train. Otherwise, what happens is your memory fills up. So either your kernel crashes or you'll get a CUDA out of memory error, in which case you'll have to restart your kernel manually and again start running everything. So try to release memory as much as you can by using these commands. Apart from that, yeah, we've already spoken about number of workers. One very important tip is if in case you get some error that you're unable to understand what is happening, you can shift from a GPU to a CPU. So have a CPU runtime, you can set device equal to CPU and then run the same cell, the error will make more sense. So in a lot of cases, when you're on GPU, there'll be some random gibberish as your error, but the minute you change it to CPU, you'll see that either your model architecture, there's something wrong where there's a shape mismatch, which is why some things are not working. So that's a very useful debugging tip. Try to do that. Apart from that, yes, always remember to checkpoint your model, try different architectures. You are only restricted to linear layers here. You can't use CNNs or RNNs, but of course, you'll be implementing that in the future homeworks. Apart from that, a lot of Piazza posts that we've seen where you get 70% locally, but then you get 5% or lesser on Kaggle. So remember to sort your MFCC files in the test data set. Ensure that you're mapping your phonemes correctly in your test functions. And a lot of you have also been getting errors that the resizing is incorrect. So in a lot of these cases, your get item or padding would be faulty. So all of this is there in the homework 1 part 2 FAQs. It's a long post in terms of the comments, but try to go through them as much as you can before you raise them, because a lot of these have already been resolved. It will save a lot of your time and you don't have to wait for anyone to come and look at your code and actually debug. But of course, for anything else, feel free to post on Piazza, attend as much OH as you can. We're happy to help you out. And yeah, I think we're done for the day for lab 2. If you have any questions, we can take them.
I have a question. Can you hear me? Hello?